All right, go.
All right. Now that we have our sample of yeast, we're actually going to count the amount of cells that are in here to be able to calculate how much we need for a new batch of beer. With our straight yeast, the slurry's very, very concentrated. There's a lot of yeast in here. It's pretty impossible to count all of these as is. So first step is the dilution. I like to do a twofold dilution, about 1 to 100 dilution. Some people like to do 1 to 1,000. Just depends on your slurry and your own preference, but that's just me. So we're taking a graduated centrifuge tube, filled up to 9 mils. This is just RO water. Okay. Do that again with the second tube.
I can't really see what you're doing.
Sorry,
but
too high.
Oh, that's good.
Good.
There you go. Yeah, so you're just filling up that little flask. Sanitization important here? Not really, because we're just counting what's there and it's not going to kill it.
Right, we're not going to use this yeast for anything, and nothing's going to get infected this quick enough to throw off the count. So we have two test tubes at 9 mils of water apiece. We're going to add 1 mil of yeast slurry to the first tube. I like using one of these guys. This is called a transfer pipette. We buy the narrow mouth tips. I like those better for the vast majority of things we do, except for this. So to turn a narrow tube into a wide tube, you just cut it where it gets thicker. Again, it's just preference. Some people like the narrow ones. Some people use different types of pipette tips, but I think
are these little disposable pipettes? Are they they're calibrated for capturing a certain amount?
They do. They have graduations on there, but I don't worry about that because I care about what the sizes are on this tube.
Gotcha. Also
with yeast, there's a lot of gas still in suspension, a lot of CO2, so it's real tough to get an accurate measurement volumetrically with yeast. So we'll suck a bunch up. Take our first tube, and we're going to go from 9 to 10. Looks pretty good.
Yep.
So now we have a 1 to 10 dilution. 1 mil of yeast, 9 mils of water. That's now a 10% dilution. Shake it real good. Then grab a new tip, a new pipette. Pull out. Again, just pull out a bunch. You don't really, doesn't matter all that much. Just more than a mil. Second tube, also at 9. We're top this up to 10. So now I've done 2 1 to 10 dilutions. 10 times 10 is 100, so this is now a 1 to 100 dilution of yeast slurry.
So you diluted 1, shook it up,
diluted it once more.
Pulled 1 out of that, put that in the other one.
Last step is we need to add a dye. We like to use one called Methylene Blue. There's further options out there. You can look into it yourself. It's really just a matter of preference.
There's a blue and a red, right?
There's 2 blues. There's a red. The red's the IUPUI. The other blue one is... I don't remember what it's called. But I like Methylene Blue. I think it works just fine. You only need about a small drop or so in the tube itself. I kind of eyeball it and I mix it together. Now methylene...
So the amount of methylene, you just want a couple drops.
Yeah.
You're not really measuring it out. It's not changing your volume.
Not enough.
This is sort of a guesstimation type work.
I look more at the color of it. That's a nice blue color. It's not navy. It's not dark. It's not like a light blue. That's a good solid just blue color. And how methylene blue works is all yeast cells will accept the dye. Living cells will metabolize the dye and turn back to a clear color. Dead cells will stay blue. So I look under the microscope, I'm going to see live cells and dead cells. Live ones will be clear, dead cells will be blue. It's pretty easy to distinguish between them.
You can remember that because you don't want to have the methylene blues.
That's right, that's right.
The methylene blues means you have a lot of dead yeast cells.
Did you do a video with the harmonica?
I wrote a song.
Yeah, I remember that.
I wrote a song about it. Want to hear it? It goes like this here. Actually, I'll play that for you later, guys. All right, so it's hard for me to see this, but
yeah, let me start this over. I forgot. Just kind of an autopilot. Wipe this off. So we use a tool now called a Hemocytometer.
hold on.
How it's designed, it's a very fancy microscope slide. It's got two segments here with the silver parts. In each of those segments, there is a grid that will break down to a 4x4 grid, which we'll use to count our yeast cells. It makes it easier to count instead of just looking at a blank space.
Yeah,
So
you can't see the grid hardly with the naked eye, but when it's under a microscope, you'll be able to.
Yeah. It gives us defined borders and specific dimensions to look at. Make sure you just two.
I have some other videos I show the class too. Okay, now how can I?
So there's, yeah, take a look at this. There's two ways to do this. You have the first option of just putting a drop right on top of the grid. And putting a cover slip on top of that. Ooh, there we go. Other options,
and that just automatically sort of smushes it down to the level that you want.
Yep. Other option is you can put the cover slip down first and use these channels on the side.
Yeah, that's what I've always seen.
To do what's called the capillary effect.
And it just sort of sucks
spreads
it up
on its
in
own.
there.
Again, matter of preference. I do think most people use the capillary to the grooves, but whatever you like to do, it shouldn't make much of a difference.
It's kind of, if you put a drop on there and put the slide on top, you sort of know that it's all over the place. The capillary effect, I guess you might not be sure.
You got trust in science.
Got to trust.
So when we look through here, do you want to take a picture of this too, Ron? We're going to see a chart that's similar to this. 4x4 grid. This is the path we use to count. Everyone's different. So something like go right, down, kind of do a zigzag that way. You go down, up, whatever is easiest to you, just as long as you do it the same way every single time. A couple things to look at. The line is this middle line here. These are the borders. This cell we count because it's right in the middle of the line. This one we do not because it's outside the lines. So the middle line is the border all the way around. Additionally, you only count the borders on the left and the top.
Two sides.
Two sides. So notice this one on here is kind of right on the border. We don't count it though because it's on the bottom. Same with this one on the right. We're not going to count that one either. I'll explain the reason for that in a little bit. Another thing to look at too is the budding cells. These are cells that are in the process of division. If the daughter cell, which is the small one, sorry about that.
Budding cell right there.
The small one is less than half the size of the mother cell, you do not count it. If it's more than half the size, you count that as two cells. See that? Right,
like that.
there? Yeah, that one, or go over this way, close it up a little bit. Down a little bit, there you go. There's a better example, yeah. So it's budding cell, yep. This one's just a little more, and it's a judgment call on your part. A little more than half the size, so I count that as two. Other one we only count as one.
Yeah. It's an estimation process and an averaging process, and it gets you in a very close ballpark.
Very close ballpark, yep. And each of these 4x4 grids, there's going to be 25 of them under this microscope in a 5x5 pattern. I'm only counting the four corners and the centerpiece.
And the middle.
Kind of like a bingo card. Four corners and the centerpiece is all I'm going to count.
Yeah.
Then I'll do a conversion to pretty much multiply by 5, and that'll help us get our actual count. You can absolutely count all 25. It's just a waste of time, in my opinion. But that's on you.
Again, it's an averaging process. So count five cubes, 5 blocks of the 25 should get you there.
Yep. Unless you're getting paid hourly, then do all 25. For me to set it up, I made 2 columns: a live column, dead column. The first grid, which is the top one, second grid is the bottom one. So you always want to do 2 counts and average your values. I'll probably just do 1 today just to speed things up. But so let me squeeze in here.
You got a counter?
Yeah, a counter, just a little clicker. They use that at bars and stuff to count people. 1 click. Then you can reset it.
Yep.
So again, some people like using 2 clickers and doing one hand live cells, other hand dead cells. I would much rather go through, count all the live cells first, then go back, count all the dead cells second. To me that's easier, but again, it's all personal preference. Set this up too so we can look in the microscope and see, get a picture of this.
And you don't have to. This is all stuff that any brewery can do, really. I mean, anyone can buy a hemocytometer, and anyone can buy a reasonable, decent microscope. So this is not hard. This is something that literally any size brewery can do. It's not expensive, it's not hard, it's not time consuming.
So the cost savings of doing your own yeast and harvesting your own yeast is insane. We'll save, we did the math one time, it's like $80,000 a year by reharvesting instead of buying new yeast.
Yeah.
So it adds up real quick.
Yeah, yeast is one of the most expensive ingredients.
Yeah, absolutely. So normally I would count all 5 things and then multiply by 5. Today I'm gonna be real lazy, just count 1 for the sake of time. Let's write that number down.
So what'd you have?
And 89 in this one, 89 living.
And 89 living.
7. And 7 dead.
7 dead.
In this one cell. So it sounds you could finagle that to make it look, get in there.
We'll see. Probably not.
Okay, yeah, there's a way to, if you get it just right, you can do it, but it's a...
I've done it before with my phone.
I have to, yeah.
I'll have to show some pictures from my phone. Yeah, it's not going to work, but that's okay. I have some other videos, and I have some pictures that I can insert to show you what Kevin's looking at inside the lens there. Okay, so what's our numbers?
All right, we'll go back this way. We'll do some math.
Oh, we gotta go to the math area.
And I'll just put my laptop up here so you can see a little bit better. All right, so one of the best things to do is make your own Excel sheet for this.
So you can track it over time too?
Yep. Exactly, yeah.
We'll try not to get your password.
Good luck, it's like stupid, yeah. What's this? So I count 89 cells. Let's say if I counted all 5 and they had that number,
So
that
is
is
this our sheet?
445. It is, yeah. So 445 living, 35 dead. We'll go with that.
Oh, so you're just multiplying.
I multiply by 5 just to get an idea what it would be if I did the full
If you
count.
counted all of them.
That's it.
Technically, you would count
I would.
the full number for all 5 squares.
Right, I'm just estimating. So we have different tabs for every beer. Sunlight, we make Osiris, Pachanga, specialty beers, all that stuff. Here's an example of Sunlight. Original gravity is 11 Plato. We do a pitch rate. A good standard pitch rate is 1,000,000 cells per milliliter of beer per degree Plato. That's a real standard rate.
Say that again.
1,000,000 cells of yeast per milliliter of beer per degree Plato. So an 11 Plato beer would have 11,000,000 cells per milliliter. We told you those numbers. That's where we started at, worked our way back or up depending on the beer and the flavor profile we wanted. There's ways you can manipulate ester production and cleanliness of a beer based on the amount of yeast you're using. So for Sunlight, we found at a rate of about 850,000 cells per degree Plato per mill works best for that beer. So that's Sunlight's rate. So it means per mill we need, what's that, 10 to the 6, 9,350,000 cells per milliliter. For a 60 barrel batch, that means we need 6.58 times 10 to the 13th, which is 6 trillion yeast cells per batch of Sunlight.
6 trillion.
Big number, big number. So how this...
We're gonna count them all.
Yeah, right.
That's what the intern does.
Oh, we're still working on it.
Yeah.
So for us, for this program to work, I'll do the date just to keep track. The batch number I pulled from, 721. So the previous batch that we used, the generation. So Gen 1 is your first time you use it again, now it's Generation 2. Gen 3, Gen 4. We typically take Sunlight up to 15 or so, because that yeast strain works really well. We have a new pitch, we started Gen 1 this week, so next week will be Gen 2. We'll go back to that. We take out to about 10 or 12, Pachanga about the same. You just kind of gotta know your yeast strains and your varieties and see how well they do.
And you got to take good care of your yeast to get 15 generations out of it. I probably wouldn't recommend that for most small breweries unless you're doing this kind of analysis and taking good care, super good care of your yeast.
Yeah.
You're getting in a really risky territory if you're going over even 5, 6, 7 generations and not doing any testing.
For sure, yeah. So we're checking the micro side of it, make sure there's no bacteria or wild yeast. We're looking at the viability every time. So with this number, I put in the 445, which is the number of cells that would be in 5. Let me zoom in a little bit. Whatever. So 445 is the number that we counted for 5 different grids there. 35 dead total. So it means a total of 480 cells were in those 5 squares on that slide.
Yep.
Comes out to 92% viability, which is very good. Very happy with that number. We want above 85, so 92.7 is great, especially for a yeast that's that old. And then the math here.
I always see, I see different people give different recommendations on that number. I've seen people say 80, 85% is fine. I've seen people say, no, it needs to be 85 or 90. I've seen some people even say they need 95%.
Yeah.
But, so everyone I think has to find what works for them.
Yep.
You guys want over 85. And I mean, we've got some of your others on screen. Looks like you got one at 75.
We do, it was a bad day.
That was a bad day. One at 81. But you know, most of them there are above 85 and 90s. So what do you do if you're below where you want to be? What'd you do on that day it was 70?
We pitch more yeast. So,
so
that's
just,
it, yeah.
I got you.
It's not ideal, but we know it works. We know it works for this yeast strain. It does not work for all yeast strains. That's the other part of having house yeast is we use it so much, we know how this yeast operates. We've taken this yeast out to 17 generations before without a problem.
Yeah.
I don't want to do that far because if there is a problem, I'd rather catch it early.
May just need to add more yeast to get to the pitch rate.
Yep. So to calculate that, I could show you examples some other time, but I just have it set up as the equation in Excel, where it takes the number of total cells, the conversion factor. Remember there's 25 grids on there, not 5, so I'm only counting 5. So I'll multiply by 5 again to get to the full 25 that are on that grid. We then have to multiply by the dilution factor, which is 100. We did 2 dilutions, a 1 to 10 and another 1 to 10. So it's the total cells times 25 times 100. And then the hemocytometer itself, the special slide we use to count, has a dilution factor of 1 to 10,000. So on that little grid, that is 1/10,000th of a mil, volumetrically speaking. So you always multiply it by, whether you count 5 cells or count 25 cells or do no dilution or 1,000 dilutions, at some point you will always multiply by 10,000. To get to the dilution factor based on the grid itself.
Yeah. And this math, there's also calculators.
There are. There's plenty of calculators online. Plug in your live, plug in your dead. Tells you what you need.
Yeah.
We then have to convert that number because that's going to give us how many milliliters of yeast we need. I hate measuring volumetrically. Again, there's a lot of gas in there, so it's real tough to get an accurate number for volume. So we always pitch our yeast by weight. The dilution we use is there is 0.002 pounds of yeast per milliliter. That was just an average we found. We took all of our yeast strains, we weighed out several examples of it, till we got the number we liked. We got a consensus number for it. It's very similar to the density of water, which you actually strip away all the protein matter and stuff, so it's not too far off from that. So we get the poundage, we then divide by the viability, because we only want to count for the amount of live cells we're pitching. So we divide this number by 0.927, so we have 92.7% viability. And that's the amount we need. We also add an additional 2.5 pounds to every brink. The reason for that is after we sanitize our brinks, we will fill them all up with a high concentration of iodine. Let it soak, let it sterilize on the inside or sanitize on the inside, push all that iodine out. If you ever looked at the bottom of a keg, there's a stem. The stem does not go to the very bottom. So there's always a little bit of iodine that's left over. We know that. So the first amount of yeast we pull off into the brink is going to die pretty much immediately. I don't know how much that number is. We've tested a few times. It's always all over the place. 2.5 is just a safe number for us that we found works really well. So that'll account for anything that dies from hitting the iodine at the bottom. Also account for anything that kind of sticks to the side. You're not going to get all of it out of the keg as we're pushing it into the fermenter. So this little safeguard for us, I recommend that number for a full 15.5 barrel or 15.5 gallon brink or half barrel brink. If you're using 6 barrel brinks, you kind of adjust that number to down to maybe a pound and a quarter. But it's just experimentation on your end to see what you actually get out of your own brinks.
Will we be able to see a yeast brink and put one up? Or at least show me the setup?
Yeah, I can do that. That's easy. Yeah.
Yeah.
That's about it. So we know for this batch of Sunlight, 61.6 pounds for 60 barrels. And that's a good way to, if you can't do a cell count, a real general formula is a pound of yeast slurry per barrel of beer. For any ale, under 15 Plato. You go above 15 Plato, you want to do about a pound and a half per barrel. Lagers start at a pound and a half and then go up to 2 pounds, which you get about 15 Plato.
Yep.
So it just depends. Big stouts, like our Imperial Stout Shatterproof, is a 34 Plato beer. We pitch at 3 pounds for that one. It's 3 million cells. It's insane. We use about 600 pounds of yeast for that beer.
Just because of the gravity.
The gravity's so high, yeah. And we want to prevent acetaldehyde and make sure we get all the ethanol, not under attenuating. Other people love under attenuated stouts nowadays, but they're wrong. So we're going to make ours the right way. Sorry.
Same goes for any of those big Belgian beers.
Exactly.
Anything you're pushing 10% ABV on.
Yep.
Make sure you got plenty of yeast.
Yeah, it's not a linear growth. It's definitely exponential. So the higher you go. So again, for Sunlight, it's about a pound per barrel at 11 Plato beer. For Shatterproof at 33 Platos, 3 times the strength, we use 10 pounds per barrel. So even though it's only 3 times bigger, we're using 10 times more yeast because that's what we need to make it a clean fermentation.
So some of that's trial and error.
Yes.
A lot of what we talked about here is trial and error. You got to know your brewery, you got to know your yeast.
Yep.
But you still need to be doing all you can to estimate it the best you possibly can and take good care of it and do your testing. Make sure you have good yeast. It's such a way to screw up beer.
Yep.
You can do everything right, and then people don't take good care of their yeast.
Yeah.
And you know, it's such an important final step.
Yeah.
Never overlook it.
I would say one of the hardest parts of being a good craft brewer is being consistent. If you make a great beer that everyone loves and they make it again and it's not as good, you're going to piss off a lot of people. So I think the consistency starts with one of the biggest parts of it is yeast health. Healthy yeast versus unhealthy yeast will make a world of difference in the finished product. So know your pitching rates, know your viability. The more consistent you can be batch to batch to batch, the better you're going to be perceived as a brewer. Not someone who just got lucky on that one batch of beer that tasted really good. So.
All right, I'm going to leave it there.
Cool. Yeah.